Hi everybody, in this video we're continuing our talk about trees by looking at spanning trees. Our main idea is that many graphs are not trees, but we can form a tree by looking at a subgraph of the connected graph. A spanning tree of a connected graph G is a subgraph that includes every vertex of G and is a tree, which gives us a few key ideas. Our spanning tree will include all n vertices of the original graph. We can't leave anything out. Because it's a tree, we know with n vertices we'll have n-1 edges and we won't have any cycles. We'll be dropping just enough edges to break every cycle and form a tree. As an example, we have the graph G that is definitely not a tree. It has 5 vertices and 7 edges. We know we should only have 4 edges for a tree with 5 vertices. Let's look at dropping the middle 3. Let's represent the dropped edges with just dashed lines. Now we have a spanning tree for our graph G. Our overall strategy for building a spanning tree is to remove edges that close a cycle until no cycles remain. Remember, you're going to keep every vertex and make sure the graph is connected. It's important to point out that spanning trees do not have to be unique. One graph could have many spanning trees. Take, for example, this graph with 4 vertices and 4 edges. We need to drop one edge to form a tree. We have choices of dropping the top edge, the right side, the bottom, or the left edge. Each of the 4 variations keeps the same original 4 vertices, we just drop a different edge, but each is a valid spanning tree. Because there are so many different spanning trees for graphs, we need to work on strategies. In the coming lessons, we'll work on cheapest connections. That means we want to find the spanning tree with the least total edge length. We could also find a shortest distance, which means we're going to link every point while keeping a total distance and routing costs low. Of course, we want to look at real-world networks like layouts for roads, power lines, and cabling with minimal wiring, and we'll look at some algorithms. Not only will we look at breadth first and depth first, we'll also look at Prim's and Kruskal's algorithms.